Everything ends. Every star you see tonight will die. Every galaxy will go dark. Every black hole will eventually evaporate into nothing. Every proton and every atom in your body will one day decay. The universe you live in is not eternal. It had a beginning, and it will have an end. The real question is not if. The question is how and when, and what the final moment of physical reality will actually look like, and what physics has to say about what comes after. These are not philosophical questions. They are scientific ones. And the answers are real, and they are among the most disturbing things human beings have ever worked out. So let us go through all of them, every theory, every scenario, from the most likely to the most exotic, from the most distant to the most immediate, from the heat death that is almost certainly coming to the false vacuum collapse that could end everything. In the next second, welcome to the most disturbing video in physics. Let us begin. Before we talk about how the universe ends, we need to talk about time, because the timescales involved in this story are so vast, so incomprehensibly larger than anything in human experience, that our intuitions about time completely fail us. 1,000,000 years is ancient to us. 1,000,000,000 years is geological. 10 billion years is older than the Earth itself. But in the story of the universe's ending, 10 billion years is barely the beginning. The universe is currently 8 billion years old. The sun has about 5 billion years of hydrogen burning left. When we talk about the death of the universe, we are talking about timescales that make 13. 8 billion years look like an eye blink. We are talking about 10 to the power of 14 years, 10 to the power of 40 years, 10 to the power of 100 years. Numbers that have no meaningful analog in human experience. Numbers so large that if you wrote them out fully, the number of digits would itself be a number larger than the number of atoms in the observable universe. And yet, these are the timescales on which physics will play out, so let us establish a framework. Cosmologists describe the future history of the universe in terms of what are called the 5 eras, 5 distinct epochs, each one defined by the dominant physics of that period, each one darker and stranger than the last. We are currently living in the Stelliferous Era, the age of stars, the time when stars form and burn and die, and the universe is full of light. This era began shortly after the Big Bang, and it will end in roughly 100 trillion years. When the last star burns out, then comes the Degenerate Era, then the Black Hole Era, then the Photon Era, then the Dark Era, and within and beyond these eras, multiple possible endings. Let us go through each one, starting with the one that is most likely based on current evidence, and then working outward into stranger and more disturbing possibilities. The most scientifically well-supported scenario for how the universe ends is called heat death, and the name is misleading. It does not end in fire. It ends in cold, in stillness, in a state of maximum entropy from which nothing interesting can ever happen again. To understand heat death, you need to understand entropy, and specifically the second law of thermodynamics, which is one of the most fundamental statements about physical reality that we have. The second law says that in any closed system, the entropy, the disorder, the number of available microstates, the thermodynamic unpredictability, always increases or stays the same. It never decreases spontaneously. Entropy is not chaos in the everyday sense. It is a precise mathematical quantity related to the number of ways a system can be arranged at the microscopic level while appearing the same at the macroscopic level. A glass of water with ice is low entropy. Everything organized. The ice cubes separate from the water, ordered, when the ice melts. Water is at uniform temperature, higher entropy, more ways to arrange the molecules while the water still looks like water. You never see the reverse happen spontaneously. You never see a glass of warm water spontaneously grow ice cubes, because that would require entropy to decrease. And the second law forbids it. Now apply this to the universe. The universe began in a state of extraordinarily low entropy. The Big Bang produced a hot, dense, smooth state, highly ordered in a thermodynamic sense, and ever since, the entropy of the universe has been increasing. Stars form and burn, releasing heat. Increasing entropy, life metabolizes, releasing heat. Increasing entropy, supernovae explode, radiating energy. Increasing entropy, everything that happens in the universe, every process, every event, every thought you have, increases the total entropy of the universe. And time in the very long run, far in the future, the universe will reach a state of maximum entropy. A state where no more entropy increase is possible, because the system has reached thermal equilibrium. Everything is at the same temperature. There are no temperature gradients, no chemical gradients, no concentration gradients, nothing from which useful work can be extracted, no energy flows, no processes occur. This is heat death, not a fire, not an explosion. A final stillness, a universe at uniform temperature, close to absolute zero, where nothing happens. And nothing can happen ever again. This is sometimes called the big freeze. And the timeline goes roughly like this. We are currently in the Stelliferous Era. The age of stars. Stars form when hydrogen clouds collapse under gravity, ignite nuclear fusion, and shine for millions to billions of years before dying. Currently, stars are forming and dying. The universe is rich and active, but this will not last. Dark energy is causing the universe to expand, and this expansion is accelerating over time. As the universe expands, the density of matter decreases. The density of gas clouds that could form stars decreases, the rate of star formation decreases, and roughly 10 to the power of 14 years from now. Approximately 100 trillion years from now, the last star in the universe will burn out. 100 trillion years is a large number. Our current age of 13, 8 billion years is 0.01% of that time. When the last star dies, the Stelliferous Era ends. What follows is the Degenerate Era, lasting from about 10 to the 14 years to 10 to the 40 years. 100 trillion years to 10 to the power of 40 years. This era is dominated by the remnants of dead stars, white dwarfs, neutron stars, brown dwarfs. These objects do not generate energy through nuclear fusion. They simply cool, slowly, over incomprehensibly long timescales. A white dwarf, the remnant of a sun-like star, is about the size of the Earth. It contains roughly the mass of the sun. Compressed to enormous density, it cools by radiating thermal energy very slowly. If proton decay does not occur first, and we will come to that, white dwarfs will cool to temperatures approaching absolute zero, becoming what are called black dwarfs, the hypothetical final state of white dwarfs, completely cold, dark, dead objects containing crystallized carbon and oxygen, floating in the vast, empty, expanding universe. The universe in the Degenerate Era is almost completely dark, essentially empty. The occasional remnant cooling slowly, separating from each other as dark energy continues to expand the space between them. The distance between galaxies will be so vast that no light from any other galaxy could ever reach any other galaxy, every island universe, alone. In infinite expanding darkness. In the Degenerate Era, very occasionally, brown dwarfs, objects that were almost stars but not quite massive enough to ignite fusion, might collide, or a brown dwarf might fall into a white dwarf. In rare cases, this could reignite nuclear fusion briefly, producing a supernova. But these events become increasingly rare over the immense timescales of the Degenerate Era, and eventually stop entirely, also in the Degenerate Era. Quantum effects become cosmologically important. The orbits of planets around dead stars are not perfectly stable over very long timescales. Quantum tunneling, the ability of particles to pass through barriers they classically should not be able to, will eventually cause orbits to decay. Planets will very slowly spiral inward or outward. The planet-star systems that survive stellar evolution will eventually dissolve. The planets drift away into interstellar space, or fall into the stellar remnant, over timescales of 10 to the power of 15 years. Even larger structures, galaxies and galaxy clusters, are not stable forever. The stars and remnants within galaxies interact gravitationally over very long timescales. This leads to what is called two-body relaxation. Stars interact and exchange energy. The heavier objects tend to sink to the galactic center. The lighter objects get ejected to larger orbits or escape entirely, over timescales of about 10 to the power of 19 years. Galaxies will have dispersed. The stellar remnants will have mostly been ejected or fallen into the central supermassive black hole. And eventually, each galaxy will consist mainly of a supermassive black hole, surrounded by a very sparse halo of ejected stellar remnants drifting outward. Then comes the black hole era, from about 10 to the 40 years to 10 to the 100 years. Black hole era begins when the stellar remnants have all decayed or been consumed. Proton decay, if it occurs, would end the Degenerate Era by disintegrating all the atomic matter in white dwarfs and neutron stars. Whether proton decay occurs is one of the most important open questions in physics. The proton is the nucleus of the hydrogen atom. Everything we are made of, every atom in your body contains protons, and as far as we know from direct experiment, protons are stable. We have detected no proton decay in any laboratory, but the standard model of particle physics does not guarantee proton stability. Many extensions of the standard model, grand unified theories, predict that protons should eventually decay into simpler particles. Positrons and neutral pions, the predicted lifetime is very long. Various gut theories predict proton lifetimes of 10 to the 34 to 10 to the 36 years or more. We have looked for proton decay in experiments like Super Kamiokande in Japan, vast tanks of ultra-pure water, watched by 10,000s of photomultiplier tubes, waiting for the flash of light that would accompany a single proton decaying. We have found nothing. This rules out the simplest versions of grand unified theories, but not all versions. If protons do decay, even slowly, then all atomic matter, everything we call ordinary matter, will eventually disintegrate. Every white dwarf, every neutron star, every rock, every grain of dust, Every atom in the vastly expanded future universe will eventually decay into radiation on a timescale of perhaps 10 to the 40 years. If protons do not decay, then white dwarfs and neutron stars might last much longer, potentially until quantum tunneling effects cause other changes. Either way, the black hole era eventually begins. In the black hole era, the dominant structures in the universe are black holes. These are the objects that remain after all stellar evolution has completed. Supermassive black holes at galactic centers. Stellar mass black holes. And black holes have a remarkable property that was discovered by Stephen Hawking in 1974. They are not truly black. They radiate. The quantum mechanical vacuum is not empty. It is full of virtual particle-antiparticle pairs, constantly popping into existence and annihilating each other. Near the event horizon of a black hole, something different happens. One member of a virtual pair can fall inside the horizon, while the other escapes. To an outside observer, the escaping particle looks like radiation emitted by the black hole. This is Hawking radiation, and it means black holes slowly lose mass over time. Very slowly, extremely slowly for large black holes, but evaporate they must. The time for a stellar mass black hole to evaporate completely via Hawking radiation is roughly 10 to the 67 years. The time for a supermassive black hole, like the one at the center of the Milky Way, is roughly 10 to the 87 to 10 to the 100 years. These are incomprehensibly long times, but they are finite. And when the last black hole evaporates, the universe will contain only photons, neutrinos, electrons, positrons, and other long-lived particles, scattered through a cold, dark, vastly expanded universe, getting further apart every instant. This is the beginning of the Photon Era, and eventually the Dark Era, where even these particles are too dilute and cold to interact meaningfully. The universe approaches, but never quite reaches, absolute zero, approaching maximum entropy, asymptotically, forever. This is heat death. This is the big freeze. This is the most scientifically well-supported ending, and it is peaceful in the most disturbing way possible. Not violent, not explosive, just cold, and dark, and still, and endless. The last thing that will happen after all the black holes have evaporated, after all the matter has either decayed or been dispersed to infinite dilution, will be a universe at a temperature not quite zero, full of photons so redshifted by cosmic expansion that their wavelengths have grown longer than the observable universe. A universe in which nothing interesting can ever happen again. This is what maximum entropy means, and this will happen unless something else gets there first. Let us now talk about what could get there first. And here is where the story gets genuinely disturbing. The second major scenario is called the Big Rip, and whether it happens depends on something we do not yet understand, the nature of dark energy. Dark energy is the name we give to whatever is causing the universe's expansion to accelerate. We do not know what dark energy is. We know it constitutes roughly 68% of the energy content of the universe. We know it causes space to expand faster and faster. And we know that the expansion is currently accelerating. What we do not know is whether dark energy is constant, the cosmological constant, or whether it changes over time, if dark energy is constant. The universe expands forever, but at a manageable rate. Heat death is the eventual outcome. But if dark energy increases over time, if its density grows as the universe expands, then something much more dramatic can happen. If dark energy increases with time, eventually it becomes strong enough to overcome not just gravity on the scale of galaxy clusters, not just gravity on the scale of galaxies, but gravity on the scale of solar systems, then planetary systems, then individual objects, then molecules, then atoms, then atomic nuclei. The force causing expansion overcomes all the forces that hold things together, and everything is ripped apart. This is the Big Rip in the Big Rip scenario. There is a finite time from now called the Big Rip time, at which the expansion rate goes to infinity, and in the final moments before the singularity, everything is torn apart on smaller and smaller scales. In the final billion years before the Big Rip, galaxy clusters are torn apart. In the final million years, individual galaxies dissolve. In the final 1,000 years, solar systems break apart. In the final months, stars and planets are destroyed. In the final minutes, atoms are ripped apart. In the final fraction of a second, atomic nuclei are torn open. And then the singularity, what current physics calls a Big Rip singularity, but cannot describe in detail. When does the Big Rip happen, if it happens? That depends on the equation of state of dark energy, specifically on a parameter called W, if W equals -1. Dark energy is constant, and the Big Rip does not occur. If W is more negative than -1, what is called phantom energy, the Big Rip is inevitable. Current observational constraints suggest W is close to -1, but our measurements are not yet precise enough to determine whether it is exactly -1 or slightly more negative. The square kilometer array and next generation surveys will constrain W much more tightly. But for now, the Big Rip is a genuine possibility. If it happens, the timeline to the Big Rip, given current best estimates of W, is somewhere in the range of 20 billion to many tens of billions of years from now, close enough that the sun may still be burning when it occurs, or may have died, depending on the value of W. The Big Rip is not the silent stillness of heat death. It is violent and sudden, a tearing of the fabric of space-time on every scale simultaneously. The Big Crunch is the time reversal of the Big Bang. It was once the cosmologically favored scenario for the universe's end, before 1998. Before the discovery that the universe's expansion is accelerating, the Big Crunch goes like this. Gravity decelerates the expansion, eventually stops it, and the universe recollapses, getting smaller and denser and hotter, until it reaches a singularity similar to the Big Bang, only reversed, going from hot, dense, energetic beginnings to cold, dark, quiet midlife to a hot, dense, violent end. This symmetry appealed to many cosmologists for aesthetic reasons, a universe with a definite beginning and a definite end, close in time, complete. But the discovery of dark energy in 1998, confirmed by Saul Perlmutter, Brian Schmidt, and Adam Riess in observations that won the 2011 Nobel Prize in Physics, ruled out the Big Crunch as the most likely scenario. Dark energy is accelerating the expansion, not decelerating it. For the Big Crunch to happen, dark energy would have to stop working, or reverse. Or the equation of state would have to change dramatically. Current evidence suggests this does not happen. But if dark energy is dynamic, if its properties can change, the Big Crunch remains possible. Some models of inflation and quantum gravity suggest that dark energy could eventually decay or change sign. In those scenarios, the crunch remains on the table. The Big Bounce is a related idea. In the Big Bounce, the universe does not simply crunch to a singularity. It bounces. The collapsing universe reaches a minimum size, determined by quantum gravity effects, and then rebounds, expanding again, creating a new Big Bang, leading to a new expanding universe, potentially just like ours, or potentially very different. The Big Bounce is motivated by loop quantum cosmology, the same framework that predicts the neutron star interior behavior we discussed in other videos. In loop quantum gravity, space is quantized. There is a minimum length, a minimum volume. Density cannot become infinite, so the singularity does not form. Instead, the collapsing universe reaches Planck density and bounces. If the Big Bounce is cyclic, if the universe bounces repeatedly, then our Big Bang was not the first, it was a bounce. And there may have been universes before ours, and there will be universes after. Penrose's conformal cyclic cosmology predicts something similar through a completely different mechanism. The universe cycles through eons, each ending in a heat-death state that is conformally equivalent to a new Big Bang, as we discussed in the multiverse video. The CCC makes testable predictions about concentric rings in the CMB, and the debate continues. Now, let us turn to something genuinely different, something that many physicists consider the most disturbing scenario on this list, and not because of its scale, but because of its immediacy. You are sitting in a metastable vacuum right now. Everything around you, every particle in your body, every photon of light, every force acting on everything in the observable universe is operating in what may be a false vacuum, a state that appears stable but is not the lowest possible energy state. The true ground state, the real vacuum, might have slightly different physics. And if that is the case, then there is some probability at any moment, anywhere in the universe, that a quantum fluctuation will tunnel from our false vacuum to the true vacuum, creating a bubble of true vacuum, surrounded by a wall of pure energy, expanding outward at the speed of light. A vacuum decay event is often called a false vacuum collapse, and it is the most violent thing that could ever happen. The bubble wall expands at the speed of light. Nothing inside can know it is coming. You cannot see it approaching. You cannot detect it. You cannot do anything to stop it. One moment you exist. The next moment, the bubble wall passes through you, and all the physics inside the bubble is different. Different values for fundamental constants, different masses for particles, different forces. Chemistry, as we know it, is impossible inside the bubble. Biology is impossible. Life is impossible. Life is impossible. The laws of physics are rewritten instantaneously, without warning. The Higgs field, the quantum field whose interactions give particles their mass, is the key player here. Current measurements of the Higgs mass and the top quark mass suggest that our universe is in a metastable state. The Higgs potential, the mathematical function that describes the energy of the Higgs field, appears to have our current vacuum as a local minimum. But there is some evidence that there is a deeper minimum, a true vacuum, with lower energy. If this is correct, our vacuum is metastable, not unstable. It will not decay immediately, but metastable, it will decay eventually, given enough time. or given a sufficient quantum fluctuation. Current calculations suggest the lifetime of the electroweak vacuum, assuming metastability, is approximately 10 to the 600 years, which is enormously longer than the heat-death timescale. But the crucial point is this: if the vacuum is metastable, the bubble could nucleate anywhere. At any time, the rate is very, very low, but it is not zero. And in an infinite universe, a bubble nucleates somewhere every finite amount of time. And once it nucleates, it expands at the speed of light in all directions, forever, consuming everything. And there is absolutely nothing any observer can do, because no signal can outrun light. You would never know it was happening. You would never experience the change. One moment there would be physics. The next moment, the bubble wall would have passed through the point where you were, and you would simply cease to exist, along with all chemistry, all biology, all stars, all structure. The bubble continues expanding forever, a sphere of dead rewritten physics, growing at light speed, swallowing the universe. This may be happening right now, somewhere in the observable universe, and we would not know for thousands or millions of years when the light from that region finally stopped arriving, giving us the first indirect evidence, and then the bubble would arrive, and there would be nothing more to know. The false vacuum decay scenario depends critically on the precise values of the Higgs mass and top quark mass. Current measurements suggest metastability rather than absolute stability, but the uncertainties are still large enough that absolute stability, no vacuum decay, remains possible if the vacuum is absolutely stable. This scenario is ruled out if it is metastable. It is real, and the particle accelerator measurements that will pin down these values more precisely are among the most cosmologically important experiments ever performed. Now let us slow down and talk about a scenario that is conceptually simpler but emotionally more immediate. And that is the possibility that we are approaching something called the Big Slurp. The Big Slurp is another name for vacuum decay, specifically for the variety where the decay is triggered not by a spontaneous quantum fluctuation, but by something that creates a sufficiently energetic concentration of energy to trigger the decay locally. This includes, in principle, in some models, certain ultra-high energy particle collisions. Though calculations suggest our particle accelerators are many orders of magnitude too low energy to trigger this. Nature provides collisions at much higher energies than our accelerators. Cosmic rays routinely hit the atmosphere with energies 10 million times higher than the LHC. And the universe has been around for 8 billion years without this happening, which itself is strong evidence that the vacuum is either stable or very long-lived. But the Big Slurp reminds us that vacuum decay is not just a theoretical end-of-universe scenario. It is an ongoing background probability, small, but real. Now let us talk about something even stranger, something that is not really a scenario for the universe's end, but a consequence of the universe's end that is itself deeply disturbing. Boltzmann brains. The Austrian physicist Ludwig Boltzmann, in the 19th century, was troubled by the second law of thermodynamics. Specifically, he was troubled by why we find ourselves in a low entropy universe at all. If entropy always increases, why does the universe have such low entropy now? Why was it born in a low entropy state? One proposal he explored, though he did not favor it, was that perhaps the universe in its equilibrium state experienced a statistical fluctuation, a temporary decrease in entropy by pure chance that created the ordered universe we observe. The problem is that the probability of such a fluctuation is astronomically low, and the probability is higher for smaller fluctuations than larger ones. The smallest fluctuation that could produce an observer, a conscious entity that could experience reality, would not be a whole universe. It would be a single brain, floating in thermal equilibrium, complete with false memories of having lived a life in a universe with a history. This hypothetical entity is called a Boltzmann brain. If the universe reaches a state of thermal equilibrium and persists in that state for long enough, quantum fluctuations could produce anything, including Boltzmann brains. And here is the disturbing logical consequence. In an eternal heat-dead universe, at thermal equilibrium, Boltzmann brains will be produced by fluctuations far more frequently than ordinary observers, like us, who evolved in a low-entropy universe. If the universe lasts long enough after heat death, then the vast majority of all conscious experiences in the history of the universe will be Boltzmann brains. And if you are a randomly selected conscious observer, and Boltzmann brains vastly outnumber ordinary observers, then you should expect to be a Boltzmann brain with false memories in a fluctuation, not an evolved being in a 8 billion-year-old universe. The fact that we seem to be the latter, the fact that our observations are consistent with being embedded in a coherent universe rather than a random fluctuation, is sometimes used as a constraint on cosmological models. If a cosmological model predicts that Boltzmann brains should vastly outnumber ordinary observers, many physicists consider that a problem with the model, not because Boltzmann brains are necessarily impossible, but because we should then expect to be them, and we are not. This is called the Boltzmann brain problem, and it is a genuine constraint on theories of the very long-term future. Related to Boltzmann brains is the concept of Poincaré recurrence. Henri Poincaré proved in 1890 that any finite system with finite phase space evolving under time-reversible dynamics will eventually return arbitrarily close to any previous state, given enough time. This is the Poincaré recurrence theorem, applied to the universe. If the universe has finite phase space, if it is bounded in some sense, then after an extraordinarily long time, the Poincaré recurrence time, estimated at roughly 10 to the power of 10 to the power of 120 years, the universe will fluctuate back to approximately its current state, or any previous state, including the Big Bang state. This would appear to be a spontaneous reversal of entropy, a universe recreating itself endlessly over timescales so vast that even the heat-death timeline is negligible by comparison. The Poincaré recurrence time is the largest meaningful number in physics, 10 to the power of 10 to the power of 120, a number so large that if you wrote the exponent in standard notation, the exponent itself has 100th has 120 digits. And the heat death of the universe, occurring at around 10 to the power of 100 years, is essentially zero compared to this time. Poincaré recurrence is not really a comfortable scenario because the recurrence time vastly exceeds any other timescale we have discussed. The universe will be dark and cold and effectively dead for times vastly longer than the recurrence time before anything interesting happens. And what happens when recurrence occurs is not a coherent re-experiencing of history. It is a random fluctuation, statistically indistinguishable from a Boltzmann brain fluctuation on cosmic scales. Now, let us talk about something completely different, something that challenges the very framing of the question, because all the scenarios we have discussed so far treat the universe as something that will end in the sense of reaching a final state. But what if the ending is not a final state, but a transition? What if the universe does not end, but transforms into something else? This is the promise and the problem of eternal inflation. If inflation is real, and the evidence strongly suggests it is, then the inflationary process may never fully stop. Different regions of the inflating background stop inflating and become bubble universes like ours. But the inflationary background itself continues, expanding exponentially, forever. From within our bubble universe, the universe will end in whichever of the above scenarios applies to our vacuum, heat death, or big rip, or vacuum decay. From the perspective of the multiverse, from the perspective of the inflationary background, our universe is not ending. It is just completing. One bubble universe among an infinite sea. Some bubble universes will be very short-lived, others very long-lived. Ours has lasted 8 billion years so far and will likely last for at least trillions more. But the multiverse, the inflationary background, the sea of bubble universes, may have no end at all. The end of our universe is not the end of everything. It is the end of this chapter in a story that may have no final page. Whether this is comforting or more disturbing depends on your perspective. Let us now talk about something that sits at the very edge of physics, beyond what we can currently compute, which is what happens at and beyond a big rip singularity, or a big crunch singularity, or a vacuum decay event. All of these involve physics at extreme scales, scales where quantum gravity becomes important. And we do not have a working theory of quantum gravity. We have general relativity, which works magnificently at large scales. We have quantum mechanics, which works magnificently at small scales. But the two theories are fundamentally incompatible at the quantum gravity scale, the Planck scale, and all the extreme events at the end of the universe, singularities, ultra-dense states. Extreme energy densities require physics at the Planck scale to describe properly. We literally do not know what happens at a singularity. General relativity predicts infinite density and curvature, but infinite values in physical equations always mean the theory is broken down. Not that infinity is real. Quantum gravity, whatever form it takes, will regularize these infinities, will give finite answers, will tell us what actually happens when matter and energy are compressed to Planck densities, string theory, loop quantum gravity, causal dynamical triangulation. These are candidates for quantum gravity theories, and they give different predictions for what happens at extreme densities. Some suggest singularities are replaced by bounces. Some suggest new universes are created. Some suggest dimensional changes at the Planck scale, but none is sufficiently developed and confirmed to give us definitive answers. The honest statement is this: we know the universe will end in some form. We have multiple well-developed scenarios for what that ending looks like. The most likely, based on current evidence, is heat death. The most disturbing, based on the possibility of metastable vacuum, is false vacuum decay. The most poetic, based on cyclic cosmology, is rebirth. And the most honest, based on our current ignorance of quantum gravity, is that we do not know what happens at the very end, at the singularity. At the final moment, we know the approach. We do not know the arrival, but there is something important to sit with here, something that goes beyond the scientific detail. Because the Fermi paradox asks where everybody is. And the answer might be, at least partly, that everybody was destroyed by the same processes that will destroy us. The same vacuum decay, the same heat death, the same big rip. These are not just our fates. They are universal fates. The laws of physics apply everywhere. Every civilization, every species, every consciousness, in every galaxy, in every corner of the observable universe faces the same fundamental limits. The universe is not hospitable to permanence. It is hospitable to temporary complexity, to brief islands of order in a vast and growing sea of entropy, to fleeting sparks of consciousness that exist for cosmologically negligible moments, and then go out. This is not pessimism, it is physics, and physics is true. And truths, even disturbing ones, deserve to be understood clearly, because understanding them changes how you think about the time you have, about what matters, about what it means to be here. Now, in the Stelliferous Era, in the age of stars, when the universe is young enough and rich enough that we can look up at the night sky and see light, when chemistry still works, when biology still works, when consciousness is still possible. We are here at the beginning, not the end, 8 billion years into a universe that will last at least hundreds of trillions of years in its active phase, possibly much longer in its dark and quiet phase. And in all of that time, the window for complex chemistry, for stars, for planets, for life, for us, is a specific era that is already underway and will one day end, but is very much ongoing. Let us now go through what we actually expect to observe in the cosmological future. Because while the very long-term future is uncertain, the cosmological future of the next few billion years is actually fairly well constrained. And there are fascinating and disturbing things coming. In about 5 billion years, the Andromeda Galaxy will collide with the Milky Way. Our galaxy and our nearest large neighbor will merge in a collision that takes hundreds of millions of years. The result will be a larger elliptical galaxy, sometimes called Milkometa. The collision will likely not destroy the solar system. The distances between stars are so vast that direct stellar collisions are rare during galactic mergers. But the gravitational disruption could alter the sun's orbit in the merged galaxy and potentially disturb the Oort cloud, sending comets into the inner solar system. In about 5 billion years, the sun will leave the main sequence. It will exhaust the hydrogen in its core and begin fusing hydrogen in a shell around the core. The core contracts. The outer layers expand. The sun becomes a red giant, expanding to perhaps 200 times its current radius, possibly engulfing Mercury, Venus, and potentially Earth. Even if Earth is not physically engulfed, the oceans will have boiled away long before. The atmosphere will have been stripped. All life on Earth will end long before the sun becomes a red giant, in about 1 to 5 billion years. The sun's luminosity will have increased enough to push Earth out of the habitable zone. The oceans will boil. Life on the surface will become impossible. The window for complex life on Earth, in the cosmic sense, is already perhaps halfway closed. After the red giant phase, the sun will shed its outer layers, forming a planetary nebula, and its core will contract to a white dwarf, a hot, dense remnant roughly the size of the Earth. With no internal energy source, it will cool over billions of years, eventually becoming a cold, dark black dwarf. In the remote future, this is the fate of our star. This is the fate of most stars. And yet, on the scale of the universe's ultimate fate, these events, the death of the sun, the boiling of Earth's oceans, the merger of galaxies, are happening in the first tiny fraction of the cosmic timeline. In the early chapters of the Stelliferous Era, long before the first era ends, long before the universe gets anywhere near heat death, in the universe of 100 trillion years from now, when the last star burns out, nothing we see tonight will remain. Every star visible to the naked eye, every star accessible to our greatest telescopes, will have burned out long before. The universe then will be as different from now as the early universe of 1 second after the Big Bang is from today. And that dark future universe will itself be nothing more than the opening moment of the vast darkness of the Degenerate Era and beyond. When thinking about the end of the universe is everything, let us return to the scenarios and rank them by scientific support, by likelihood, and by what they mean for the question of ultimate fate. Most likely, heat death, supported by the second law of thermodynamics, one of the most fundamental laws in physics, and by the confirmed acceleration of cosmic expansion. If dark energy remains constant, if nothing prevents the approach to maximum entropy, Heat death is coming on a timescale of at least 10 to the 100 years, second most likely. Big rip. If the equation of state parameter W is more negative than -1. If dark energy increases, the big rip follows inevitably. Current observations are consistent with W equal to -1, but do not rule out phantom energy. More data is needed. Depends entirely on the nature of dark energy, which we do not understand. Genuinely possible, false vacuum decay. If the Higgs vacuum is metastable, which current calculations suggest, then vacuum decay will occur eventually. The question is timing. Current calculations suggest the lifetime is extremely long, but the event is random. Could happen at any time, including very soon, though probability is very small. Genuinely possible, big crunch. If dark energy changes behavior, if quantum gravity effects alter the expansion, a collapse is possible. Current evidence argues against it, but our ignorance of dark energy makes certainty impossible. Possible under specific frameworks. Big bounce cyclic cosmology requires quantum gravity theories that are not yet fully developed. Loop quantum cosmology and Penrose CCC are internally consistent but not definitively confirmed. Speculative but serious. Boltzmann brains. Not really a scenario for the universe's end, but a consequence of heat death with eternal persistence. Raises deep problems for cosmological theories. Increasingly speculative. Poincaré recurrence follows from basic mathematics applied to bounded systems. Whether the universe qualifies as bounded in the relevant sense is unclear. Most exotic. Scenarios involving quantum gravity physics at singularities. What happens at the big crunch singularity? At a big rip singularity? Genuinely unknown. Awaiting a theory of quantum gravity. Now let us talk about what this all means, not just scientifically, but as a matter of understanding what we are, and where we are, and when we are, and when we are. We exist in the most interesting era of the universe's history. The Stelliferous Era, the age of stars, is the only era in which complex chemistry is powered, in which nuclear fusion produces the energy needed for biology, in which the temperature differences that drive structure formation exist. In the Degenerate Era, in the black hole era, in the dark era, in the heat death universe, there are no stars, no planets, no biochemistry, no life. Not because life chose not to evolve, but because the physics does not permit it. The window for life, at least for life as we know it, is bounded. It opened when the first stars formed. It will close when the last stars burn out in roughly 100 trillion years. That is a long window, but it is not infinite. And within that window, we are near the beginning. The universe is only 8 billion years old. Most of the Stelliferous Era has not yet happened. Most of the stars that will ever exist have not yet formed. The universe in 50 trillion years will still be full of stars. We'll still have planets. We'll still potentially have life. The universe is young, and we are among the earliest conscious observers in the history of the cosmos. Not necessarily the first. Other civilizations may have arisen and died long before us, but early. In the cosmic sense, we are infants. And perhaps that is both humbling and significant. Humbling because we know almost nothing. Significant because whatever we learn, whatever we build, whatever we understand, happens early. When it can still matter. When the universe still has the energy to support consequences. The question of how the universe ends is not a question about the distant future. It is a question about the structure of physical law, about the fundamental nature of reality, about what kind of place we inhabit, and the answer, across all the scenarios, is the same. We inhabit a universe that is temporary, that had a beginning, and will have an end, in which the laws of thermodynamics are inexorable, in which entropy wins, eventually, in which the complexity we see, the stars, the galaxies, the chemistry, the biology, the consciousness, is a temporary elaboration, a transient structure, a brief, beautiful deviation from the long-term trend toward maximum entropy. That is what we are, beautiful deviation. A moment of improbable order in an ocean of growing disorder, and that fact that we exist in the window, that we are here. Now, in the Stelliferous Era, in the age when chemistry works and stars burn and life is possible and consciousness can ask questions, is not a given. It is a coincidence of timing so extraordinary that the probability of it happening by chance is almost too small to calculate. Or perhaps it is not a coincidence at all. Perhaps, as the anthropic argument suggests, the universe can only be observed by observers that evolved in the right conditions. And the right conditions only exist in the Stelliferous Era. We are here because this is when observation is possible. But whatever the reason for our presence, the fact of our presence now, in the brief cosmic window when complexity is possible, deserves to be understood and honored, not with despair at its transience, but with the seriousness that the physics demands. Every atom in your body was forged in the interior of a star, and will one day, in an unimaginably distant future, either decay away through proton decay or be dispersed into the infinite expanding cold of a heat-dead universe, or be ripped apart by dark energy, or be written when a vacuum bubble passes through. We do not know which ending awaits our atoms. We do not know the final chapter of the universe. But we know we are in the middle chapters, the interesting chapters, the chapters when there are atoms and chemistry and stars and minds to ask the question, and the fact that minds exist to ask the question in this era. Before the last star burns out, before the last black hole evaporates, before the universe reaches the stillness of heat death, is perhaps the most remarkable fact in physics, not the end, but the now, not the final entropy, but the temporary order, not the darkness ahead, but the light we are in, this moment, right now, is the universe being alive and knowing it, and soon, perhaps 5 billion years, perhaps 100 trillion years, perhaps 10 to the 100 years, perhaps in a quantum fluctuation in the next second, it will be over. All of it, every atom, every star, every thought, every memory, every discovery, gone or transformed beyond recognition, beyond the physics we know, but right now, it is here, and we are here, and we know that it will end, and that knowledge, that ability to look into the deep future and see the physics, is perhaps the most extraordinary thing the universe has ever produced. A temporary arrangement of atoms, looking out at the cosmos and understanding, in principle at least, how it ends. The universe will end. Every theory agrees on that. They disagree only on the mechanism and the timing and what, if anything, comes after. And while the details remain uncertain, and while quantum gravity has not yet given us its final word, and while the nature of dark energy remains mysterious, the broad outline is clear. We are here, briefly, in the most interesting era, asking the most important question, and we do not yet have the answer, but we are getting closer. One experiment, one observation, one calculation at a time, and that the search, the asking, the not yet knowing may be the most beautiful thing in a universe that is running down.